So far, we have talked about the diffusion in so-called single phase. Single phase. Today, we are going to talk about the diffusion process that involve two phases. Two phases. So, what are we looking at? We are looking at a binary phase diagram. Okay, one side pure A, the other side pure B. We have alpha, single phase solid solution. We have beta, single phase solid solution. On the other side, we have gamma, something kind of like higher temperature, a solid, the complete solid solution above certain temperature. Of course, further above that will be liquid phase. Let's neglect that. Okay, here would be so-called single phase region. On the right side, it will be two phase region. Single phase beta. In between alpha and beta, below this so-called eutectoid temperature, this is what? Two phase region of alpha plus beta, right? That's what you learn in thermodynamics. Here is also two phase region. One is alpha, the other one would be gamma, right? And then what you learn in thermodynamics for the phase diagram to interpret, if I'm within a system composition is within here under equilibrium, the composition for each of the phase would be decided by the so-called tie line, right? The composition for each of the phase, I'm pointing to here, the composition for the alpha phase will be determined by the crossing point, right? Of here. The composition for the gamma phase would be determined by this line, right? Under what condition? Equilibrium condition. So now let's consider the diffusion involving two phases. Okay. Let's consider we put two pieces of material together. One piece is pure alpha. Where is pure alpha? On this phase diagram. Here, right? Pure A, actually, I would say pure A. The other phase would be gamma, but at the composition that I label as CS here. Here, we put two pieces of material together, join them tightly. At what temperature? At the T1 temperature. Okay, one piece here, one piece here. And then if we something like that, I have alpha, I have gamma, okay, and naturally, I'm kind of drawing a interface. I'm drawing an interface between alpha and the gamma. Let's say our system is overall composition is somewhere here. Sorry, somewhere here. On the equilibrium condition, we should end up with how many phases? Two phases, right? On the equilibrium condition, we would end up with two phases. But the two phases, the composition of those two phases would be determined by, as I mentioned, the so-called intercept of our temperature isothermal line, tie line, with the phase boundary lines, right? That will be alpha will be here, beta will be here. But the diffusion would also happen in this process, and that's what we're going to think. We consider or make assumptions again. The first one would be, okay, slow diffusion process. We assume, okay, under this condition at T1, the diffusion is relatively slow. Why? Because we are assuming A and B are similar size. Probably substitutional solid solution. They are similar size. Diffusion would be slow. On the other hand, we assume what? Read to yourself. So-called fast phase transformation at the phase boundary, at the interface, at the interface between the two different phases. If there's any reaction that would happen or rearrangement of the crystal structure, it happens pretty fast. Okay. Under these conditions or these assumptions, slow diffusion, fast interfacial reaction, we can say the system would achieve so-called local equilibrium. Local equilibrium. What does that mean? Local equilibrium. I have gamma phase here. I have alpha phase here. Local equilibrium means right at this interface, assuming my temperature is uniform and it's all at T1, right at this interface. Right at this interface. The composition for each of the phase at this interface would be determined by equilibrium, by the phase boundary. On the other hand, we said in the beginning, we said this piece of alpha is pure A, right? At the beginning, we said this piece of alpha initially is pure A, which means far away from the interface alpha would have the composition of what? Pure A, right? Similarly, for gamma, we said initially its composition is CS, which means slow diffusion, which means far away from the interface. The gamma phase would have the initial composition of CS. Make sense? Because we are assuming what? We are assuming slow diffusion, but fast reaction at the interface, which means at the interface on the alpha side, look at what I label. CB alpha means what? The composition very concerned with B. Okay. In which phase? CB alpha means CB, right? Is the composition of B in which phase? Alpha phase. It's going to be determined by local equilibrium. Where CB alpha? It's going to be C, right? The temperature tie line or isothermal temperature line intercept with the phase boundary. Which phase boundary? Alpha phase boundary. That will give us the so-called CB alpha. Make sense? CB alpha. Again, what does CB alpha mean? C for concentration, B for your solute atom. Alpha means I'm concerned with the concentration in which phase? Alpha phase. Okay, it's going to be determined by the intercept of the temperature line with the phase boundary. End up is here. Okay, then on the other side of the phase boundary, remember phase boundary at least involve two phases. On the other side, on the gamma side of phase boundary, I would have CB gamma. Again, CB gamma is for the concentration of solute atom B, but in which phase? Gamma phase. It's going to be similarly determined by the intercept at this temperature with the phase boundary, but the boundary we are talking about gamma phase boundary, right? It's going to be here, which this guy. Make sense? So local equilibrium means I have two phases at the boundary because slow diffusion and fast interfacial reaction. Right at this boundary, the composition for each of the phase right at the boundary will be determined under equilibrium through the phase diagram. Okay, CB alpha for here, CB gamma for here. Okay, since you have a question. Okay, so now let's consider something. We learned in thermodynamics a so-called phase rule. What is phase rule? We listed here. F equals C minus P plus 2. That's what you learned in thermodynamics, right? C, F, and P, we're going to talk about them again here. F is the so-called degree of freedom. What does degree of freedom even mean? It means the number, read it to yourself, the number of variables What are the variables? Temperature can be a variable. Pressure can be a variable. Composition of a variable. Typically, we are talking about the intensive parameters, not the extensive, not the molar amount. The intensive, that tells you something about the system nature, temperature, pressure, exact composition. The degree of freedom, which means the number of variables that can change independently. That's F. Okay? What about C? C is the number of components. I put a bracket, pure component. For alloy, this can be for an alloy, this can just be pure element A, pure element B. But we may have so-called a pseudo-binary case. We may have one compound on left side, another compound on the other side. That can also be treated as a component. So number of pure components. It could be pure nickel, pure copper. It could also be pure aluminum oxide, pure chromium oxide. Make sense? Even though aluminum oxide has how many elements in it? 2. Chromium oxide also has 2 elements. Okay, those two would be together as a pseudo binary. Okay, C, number of pure components. P means the number of phases, right? That's what you learned in thermodynamics. Okay, and based on this, if we are looking at the constant temperature of T1, the temperature that we are interested, constant temperature T1, and the constant pressure, let's say ambient pressure, 1 atmosphere, 1 bar. Okay, for simplicity, let's look at the constant temperature and constant pressure. It means what? Okay, it means if we are within single phase region for binary system. For binary system, when looking at what we are looking at, binary, which means C is what? Binary system, C is 2, and the single phase, which means P equals 1. 2 minus 1 plus 2, totally 3 degree of freedom. But on the other hand, if we fix temperature at our chosen temperature T1, if we also fix pressure at our ambient temperature atmosphere, then we are only left with 1 degree of freedom, which means there's only one intensive parameter that can change. And what is that intensive parameter? It will be the composition, X, or molar fraction. From pure A to pure B, molar fraction of B can change independently. Can change independently or continuously. Okay? Within the single phase region. What does that mean? It means, okay, if I'm looking at this in within pure alpha phase, at this temperature, at 1 atmosphere, the composition within this alpha across this material can change what? Independently. It can change continuously. Make sense? Similarly, if I'm looking within the pure the gamma phase, not pure, the gamma phase, the composition can change what? Independently, continuously within the gamma phase. Make sense? On the other hand, if we look at two-phase boundary, where is that two-phase boundary? Right at this interface, right? That's our phase boundary interface between alpha on one side, gamma on the other side. Right in this local region, not a mathematical zero boundary. It's a finite area, kind of within a finite area, very close to this boundary. We would have what? Read. Two phases coexist, right? Right at this interface. I would have alpha on one side, gamma on the other side. The two phases are in close contact. I'll put another way, the two phases are coexisting in that local region. Which means locally I would have P equals what? 2. Based on our phase rule, C is still 2 because binary. P is 2 plus 2. Totally, we only have 2 degrees of freedom. But then we said if we are looking at a fixed temperature, because we are doing our diffusion at a given temperature of T1, right? And we are doing it at constant pressure, 1 atmosphere, then we are left with what? 0 degree of freedom. What does that mean? That means under that condition, in that local region, there's no intensive parameter that can change. Intensive parameter means the composition. That's the only remaining intensive parameter, because temperature you chosen T1, pressure you choose 1 atmosphere. At that local region, where? Only here, very close to this local region, the remaining intensive parameter composition or molar fraction, atom molar fraction, cannot change within each of the phase. Composition for each of the 2 phases cannot change. And what are those 2 phases? Composition for those 2 phases. We just said the composition for those 2 phases are determined by the intercept with what? The composition for alpha phase at here is determined by the intercept with the phase boundary, right? On one side. On the other side, it's determined by intercept of isothermal temperature with phase boundary that gives this guy. These 2, which means here and here, the composition for these cannot change when the 2 boundaries are coexisting. I'll put it another way. We are going to draw what versus what. We are drawing, look at this coordinate frame. We are drawing what versus what. Location, X for location versus composition or concentration. Pay attention. I'm drawing the other way, which means now my horizontal axis is C, which matches the phase diagram, right? I'm drawing this purposefully so that my composition axis matches the base for the phase diagram, because the bottom of the phase diagram is our molar fraction, right? Our composition. The vertical axis here is x for location or distance within the material, which the distance matches our actual sample that I illustrate here. You see the point? So you have to kind of, for typical, you have to rotate your head, turn your head a little bit to look at that plot. Make sense? You look this way instead of looking this way. Make sense? And then, if I'm going to plot the change of composition across this system, 2 material, right, 2 phases, do you see the composition roughly changes something like this at a given time t? Where is our interface at a given time t? Interface corresponds to interface. And which part is our alpha phase? From here to here, right? From here to here. And let's think. Within alpha phase, our very far away from the interface, the concentration of Cb is what? 0. Why is Cb 0 on this plot? Left or right? Cb 0 on this plot is all the way towards left, correspond to POA, right? Which means deep, very large in X, my composition is what? Cb is 0. Make sense? And then from here to here, because this line corresponds to what? Our so-called phase boundary or interface, right? From here, X, all the way to here, I'm within what phase? from here to here, from here to here, and within alpha phase. The composition would change from 0 when P is 1 continuously, independently, from 0 all the way to here. Make sense? And here is what? You rotate your head. This guy corresponds, you look at here, it's our CB alpha, right? What is CB alpha? It's determined from here. I draw it all the way down to here. Make sense? And then you go across this interface suddenly within a very short distance. Make sense? From lower alpha to top gamma, I'm changing in terms of distance by a very short distance, which means mathematically it's kind of a jump. Make sense? And then the other side of the interface, I'm at which phase? The other side of the interface, I'm now in gamma, right? From here to here, from 0 to here, I'm in gamma phase. And far away from the interface, the gamma concentration is CS. Make sense? Because we said slow diffusion, far away from the interface, the concentration has not really changed. And then at the interface, the gamma concentration of CB would be determined by intercept between isothermal and phase boundary, which go down to here. Make sense? That's how you view it. You kind of like look at the concentration, you have to tilt your head the other way to look at the concentration. Make sense? So that the location matches your actual sample. And then as time goes on, let's say we have the boundary moves downward, which means the gamma phase is getting more and alpha phase is getting less. That's what we call phase transformation. Okay? And let's say over a certain time, it moves from the original location in red to this location in blue. But as it moves, the local composition in alpha phase is still determined by equilibrium. It's still CB alpha. Again, CB for concentration of B atom, but the superscript alpha means it's alpha phase. On the other side of the interface, we have CB gamma, solute atom, but in gamma phase. It's still here, right? And these two concentration actually hasn't changed. It's still CB alpha, CB gamma. But then if we're going to plot the concentration profile again across the material, now let's see if this makes sense to you. The blue one. Very far away from the interface, deep in gamma, the concentration starts still at CS, right? And then goes continuously at interface. Now from here all the way to here is gamma phase. And then at the interface we have a sudden change in what? Concentration, because we are going from what phase? Gamma phase into alpha phase. And then once we are in alpha phase, we change, the concentration will change continuously. And when it's very far away from the interface here, the concentration is 0. Make sense? Okay. So that's the kind of like how does this move. And then this would be the activity plot. We are plotting again activity A for activity for solute atom versus location. Again, it's plotting in the other way. And within at the time t for the red one, within alpha, I have continuous changing activity, and then within beta, within gamma, I have continuous changing activity. And they have to match here because locally I have equilibrium. Make sense? Locally they have the equilibrium. Similarly, at the time t plus dt, As time t plus dt, the time interface moved by dx, the concentration profile would change a little bit, but they still have to connect at well at the interface. While within each of the phase, they have to be continuous. Okay.